That would be. Let's talk about heat capacity, specific heat, and calorimetry. Here's what the IB folks expect you to know on this subject. Topic 3.2.1, define specific heat capacity and thermal capacity, and solve problems involving specific heat capacities and thermal. This is kind of the major thing of this unit that you'll do a lot of. So let's talk about it. This first part's a little bit of review. Heat, internal energy, and temperature. How would you define internal energy? The internal energy of an object.
The sum of potential and kinetic energy in this object.
All right, beautiful. Okay, the sum of all the energy of the molecules, including potential and kinetic. The kinetic energy is their motion. Where does the potential energy come from?
Gravity.
Okay, excellent. They're not really gravity, because gravity is irrelevant on an atomic scale. The masses are so small that gravity is pretty much negligible. But instead, there is electrical forces in between atoms and molecules, and there can be potential energy stored in that electrical force. Okay? Great. Then how would you define temperature? We've done it. Let's do it again. Temperature.
The measure
Of?
average.
There you go. Okay. That is temperature. It's a measurement of on average, how much kinetic energy the atoms or molecules of something has. Therefore, how would you define heat? What is beautiful? The amount of energy transferred from one object to another. And what is it that determines the direction of heat flow? So temperature. It flows from hot to cold. Therefore, the temperature determines what direction energy will flow. Beautiful.
Did you say that it does depend on the amount of energy?
So you're out hiking on a glacier, carrying your cup of tea. Which has more internal energy, the glacier or the cup of tea?
Glacier. Cup of tea.
The glacier, due to its mass, it's going to have a lot more energy, right? Which has a higher temperature? Cup of tea. When you trip and spill your tea, does energy flow from the glacier to the tea or from tea to the glacier? Okay. So the energy doesn't determine the direction of heat flow. It's the temperature that determines the direction of heat flow. Okay? Make sense? Great.
But if the tea had so much energy.
So in the 1700s, you guys, there was tons of research done in the realm of heat. And a long time ago, this idea of what makes something hot and makes it cold, it was imagined that it was some sort of a fluid. That they knew it kind of could be transferred. They knew it could flow. They even gave it a name. They called it caloric. And they basically just said, hey, if you have a lot of caloric, you must be hot. And if you don't have a lot of caloric, you must be cold. And there you go. They did some measurements and stuff. And we have units that still deal with this word. The calorie. You've probably heard of the calorie before. And the calorie is the commonly used unit of heat transfer. 1 calorie is the amount of energy or the amount of heat that is needed to raise 1 gram of water 1 degree Celsius. Now recognize this is a lowercase c. It's a lowercase c calorie. Okay? The pure definition of a calorie is that it's 1 degree Celsius, and specifically from 14.5 degrees centigrade to 15.5 degrees centigrade. Because technically at different temperatures it takes slightly more or less energy, but that's not that important really. Now a capital C calorie is a food calorie. Those of you that diet and worry about your figure think about calories all the time, and you're thinking about food calories, and those are 1,000 scientific calories. Okay, it's actually a kilocalorie, what we call a food calorie. So a food calorie is the amount of energy that would raise a kilogram of water 1 degree Celsius, or a gram of water 1,000 degrees Celsius. That's a lot.
That's interesting.
That's a lot. Yeah. And finally, the SI unit for heat, the more metric unit for heat is the joule. Okay? We talk about heat being transfer of energy, and we've always talked about energy being measured in joules. Rarely do we talk about energy being measured in calories. But in this heat unit, sometimes that happens. Okay? So in the 1800s, there was this scientist by the name of James Prescott Joule. And you know he did something good because we've been talking about joules for the past half year or so. So he has a unit named after him. Therefore, he figured something out. Okay? You don't get something named after you until you do something good. And I'm looking forward to the day when one of you guys gets a unit named after you, because that'll be cool. And I'll be like, I taught that person. That was pretty cool. Okay? So James Prescott Joule, he made an incredible discovery, and the main discovery he made was that he recognized that heat is another form of energy. It isn't this weird caloric material. It's actually just a form of energy, just like work is a form of energy. There's a relationship. And he developed an experiment that really is one of the classic experiments in physics. There's a few of them that I'll show you throughout the course, and I think I probably showed you one last year. Remember the one where Cavendish measured big G with the cable and the rod and the big spheres? That's a classic physics experiment.
Did we do that?
So with Joule's measurements, he discovered, wow, okay, he discovered that there is this thing called the mechanical equivalent of heat. And what they were calling a calorie before, okay, the amount of energy needed to raise 1 gram of water 1 degree Celsius, Joule discovered that it's 4.186 joules per calorie. Maybe Joule didn't discover that. He discovered that there was a relationship between energy or work and heat, and we now call it the mechanical equivalent of heat, that 4.186 joules of energy is the equivalent of 1 calorie, or 4.186 joules of energy will heat 1 gram of water 1 degree Celsius. Okay? A food calorie, therefore, is 4,186 joules. So you can do all kinds of conversions now. You can look at your Snicker bar, see how many calories it has, and figure out how much work it should be able to do if you can convert it all into energy. Right? That's the kind of stuff we can do.
That's a big task to accomplish.
So heat is a form of energy transfer, and there are 3 main forms of heat transfer. Luke, there's 3 main ways in which heat gets transferred. What are those?
And radiation.
Excellent. Convection, conduction, radiation. Okay? You did. Now, this used to be part of the IB syllabus. They took it out of the IB syllabus, but you still should kind of know these general forms. For convection to take place, you need to have a fluid, something that can flow. And if you think about it, when a fluid heats up, it expands and tends to be less dense, and it will rise. And that will distribute energy. Okay? Imagine you heat the air down here at the bottom of the atmosphere. It gets hot, it rises. It carries that heat, that energy with it into the upper atmosphere. That's convection. This is how the weather is driven on Earth. It's how plate tectonics is driven on Earth. It does a lot of things. Conduction, on the other hand, you must have contact. You must be touching. And by physically touching, molecules that are hotter will be moving faster, and they will collide with the colder molecules and give them energy because of the collision, and therefore that energy will be transferred slowly or fastly through the material, depending on whether or not it's a good conductor of heat. Finally, radiation is just anything that has temperature radiates energy in the electromagnetic spectrum. You guys radiate energy in the infrared. You can feel it if you put your hands up next to your face. You can kind of feel heat coming off of you. That's radiating off of you, okay? Like a fire. You walk into a room. If you stand above a fire, that's convection, right? The heat's rising. But if you're beside a fire and you're warm, that's radiation, okay? You walk into a kitchen and you know the oven is turned on. That's radiation. You can feel the radiation coming off of it, okay? Okay, here's what we really need to be talking about, you guys. Other than space and the thermometers and vacuums. Specific heat. What's about to die?
Hey, there's the warning.
No. Specific heat is represented by the lowercase letter c in mathematical equations. You might have recognized that we just talked about lowercase c as a unit, but now we're talking about a variable in an equation. You guys with me there? We use letters in variables, we use letters in units. The specific heat, this was a lot of the stuff was researched in the 1700s, and what they recognized is in order to change the temperature of something, there are a few factors that determine how easy or how hard it is to change the temperature of an object. One factor is how much of that stuff you have, its mass. Another factor is how much temperature you want to change it, okay? And then the third factor has to do with the material itself. There's a property of a material that determines how easy or how hard it is to change its temperature, okay? And that property is called specific heat. It's unique to each material, and basically, the equation that you will use frequently in this unit is Q equals mc delta T. Okay? Q is heat. It's measured in joules. Q is heat, measured in joules. M is mass, measured in kilograms. T is temperature, measured in Kelvin. And C is this thing called specific heat. All right? The specific heat of a material is how much heat it takes to raise 1 kilogram of that material 1 Kelvin. Okay? What's that? T is temperature. The specific heat of a material is how much heat it takes to raise 1 kilogram of that material 1 Kelvin. And specific heat is measured in joules per kilogram Kelvin. Okay. All right, let's try a little practice problem. There's a little practice problem. So you've got 650 grams of aluminum. It cools from 80 degrees Celsius to 20 degrees Celsius. There's the specific heat of aluminum, 910. Please tell me how much heat is released. How many joules of energy are released by that aluminum when it cools from 80 to 10 to 20 degrees? So the correct and true answer is 35,000 joules. Okay, not negative. That's just a bullet. Okay. I mean, it could be negative. That would just mean that it loses that much energy instead of gaining that much energy. Okay. And the reason it's not 35 million or whatever the other one is, please remember you have to convert grams to kilograms. So it should be 0.65 kilograms. Okay. All right. Beautiful. Now, water is a really unique substance. It is one of the highest specific heats of all materials. It's awesome. This is why we use water in heating and cooling, because it takes a lot of energy to change its temperature, and if we let it cool, it releases a lot of energy. We use water in cooling systems for cars, right? And we add some other chemicals to give it a wider range of freezing and boiling points. But water is awesome. This is why cities near oceans don't usually get really freezing and don't usually get super hot. They're usually kind of mellow because of the ocean absorbing so much energy and releasing so much energy. Yeah, but the specific heat of water is a number that will come up a lot. It's 4,186.
Wait, that's the same amount of joules that is required.
It's kind of weird. Yeah, okay.
Oh, wait.
It's kind of weird. So, specific heat of water, 4,186. So here's a practice problem that you could try, and if we had time, we'd try it, but we're not going to try it today because we're running out of time. But if you're at home, you should try it. Give it a try. All right. Okay. First of all, yeah, there we go. It's not a lot. Notice that we started at 12 degrees Celsius and we ended up at 12.26 degrees Celsius. So if we sit a solar water heater out in the sun, it's got 50 kilos of water all day long, it doesn't heat up that much because water has such a high specific heat. Okay? If you have a low specific heat, it would heat up much more readily when it's absorbing energy. Now, heat capacity is very similar to specific heat. It just takes into account the mass as well. Okay, specific heat tells me something about an element, about how much energy it takes to warm it or cool it. And heat capacity is that particular element plus how much of it I have. Okay, so if I have a cup of water and a big bucket of water, they both have the same specific heat. But my bucket of water has a greater heat capacity because it's got more mass. Okay? So to find heat capacity, basically all you do is take specific heat and multiply it by the mass of that material that you have. You don't do a lot of this, but it's just something to think about because it can help make complicated equations a little bit easier. It's big C, and yeah, it's the mass of the material, so it's kilograms times specific heat, so it's going to be joules per Kelvin. Joules per Kelvin. I know. The reason this sometimes is useful is if you have multiple materials, let's say you have an aluminum cup with water in it and you want to do some calculations, you can figure out the heat capacities of the water and the cup, and then if you know how much its temperature changes, the math is much easier to deal with. Luke.
Are our internal temperatures like pretty stable because we're mostly made out of water? Or does that have?
Calorimetry is what we're going to get into, and calorimetry is actually the quantitative measurement of heat exchange. You have two objects at different temperatures. Heat flows from one to the other. If you measure that stuff, we call the process of doing that calorimetry. And you guys know that there's this law of conservation of energy. If I have isolated systems at different temperatures, heat will flow between them, okay? Or if I have an isolated system, heat will flow between them until the temperatures equal out. And then there will be thermal equilibrium. The amount of heat gained by one object will equal the amount of heat lost by another. Therefore, MC delta T gained by one object will equal MC delta T lost by another. Okay? Because that's the last slide. Okay, review. How do you do that? That would be the tool, but what's the equation? Excellent. Q equals MC delta T. How about this one? What is C? And what does that mean?
How much it takes to change 1 kilogram of water, 1 degree Celsius, and 1 Kelvin.
And how much what that it takes? How much energy or heat? Excellent. Okay. Specific heat is 1 kilogram. Yep. Okay.